All right, welcome everyone. So in this video, I want to revisit our notion of linear transformations and expand this. Before, when we were talking about linear transformations, we were mapping from Rn into Rm. So we were thinking about vectors in like the real vector sense. But now that we can think of vector spaces as collections of more abstract things, maybe our vectors are actually matrices, or maybe our vectors are actually functions, we can generalize this notion of what a linear transformation is, not just from Rn to Rm, but from some general vector space V to some other general vector space W. So we can define a linear transformation from vector space V into vector space W as a rule that's going to map each vector x in V to a unique vector that will just denote t of x in W, such that for all vectors u and v in our domain, the vector space V, and scalars c, that when I take the transformation of u plus v, it's the same thing as taking the transformation of u plus the transformation of v. And similarly, we can pull out multiplication by a scalar. So the transformation of scalar c times vector u is going to equal c times the transformation of vector u. So this is the same definition and the same properties that a linear transformation needs to satisfy. The only distinction here is that these vectors u and v, these can now be more abstract things. They could be a matrix, they could be a function, or they could just be vectors like we've been dealing with. So let's take a look at some more general examples. So for example, I can think of this map T, this transformation that's mapping P is the set of all polynomials with the usual addition and scalar multiplication into the vector space R of real numbers with the usual addition of numbers and scalar multiplication. So now what you need to check, and be careful here, is that the addition operation depends on where we are. So when I'm adding u plus v, u and v, these are vectors in the vector space V, so I should be using the addition defined here. When I'm adding tu with tv, now these are vectors that live in vector space W, so I should use the addition that's defined in vector space W. And so for this case, where we're going to map from polynomials into the real numbers by taking that polynomial and integrating it from 0 to 1, right? And so after I evaluate this definite integral, we get a real number. So that's why our codomain is R. Well, we can check that, does this map satisfy these two properties? So first, if I'm taking two vectors in my vector space P, that might mean polynomial P of x plus Q of x. And so by definition, what this map would do is it would integrate P of x plus Q of x dx all over the interval from 0 to 1. And as we know from properties of integration, we can break up sums inside and outside of integral. So I can write this as the sum of the integral of P of x from 0 to 1 plus Q of x from 0 to 1. And this is by definition T of Px plus T of Qx. And now let's check the second property, which is if I apply this transformation to some scalar c times some polynomial p of x, well then by definition we're going to integrate c times p of x over the interval from 0 to 1, and we can pull out constant multiplication from inside of integrals. So this equals c times the integral of p of x from 0 to 1, and that is equal to c times the transformation of p of x. So both of those properties check out for this map between vector spaces, where now this domain is actually not a set of vectors that we might think of in the literal sense, but we're thinking of vectors now as the set of all polynomials. And let's take a look at another kind of non-standard example. So now let's take a look at a linear transformation that's mapping from the vector space of all 3x3 matrices, where now our addition is matrix addition and our scalar multiplication is the usual multiplication of a matrix by a scalar. And we're going to map from these 3x3 matrices to the vector space R with the usual operations, where we're going to take a matrix A and map it to the sum of its diagonal entries. So A11 is the first diagonal entry, A22 is the diagonal entry in row 2, and A33 is the diagonal entry in row 3 of matrix A. So let's see why these properties 1 and 2 work for this map. And so first, if I were to take two 3x3 matrices that I'll denote A and B, and if I first add them together, then the diagonal entries of the matrix A plus B would be A11 plus B11. That's the first diagonal entry. A22 plus B22 would be the second diagonal entry, and A33 plus B33 would be the third diagonal entry of the matrix A plus B. So this map would then say, take this matrix A plus B and add up the diagonal entries. So that's where this sum on the right side comes from. And just by rearranging these terms, right, we can see that this is equal to what I would get if I took the transformation of A. I would get A11, A22 plus A33 plus the transformation of B, which would be B11 plus B22 plus B33. So we can see that, yes, the addition property works, that we can split up addition through this map. And let's check the scalar multiplication condition next. And for the scalar multiplication, if I first multiplied C times matrix A, then every element of matrix A gets multiplied by the scalar C. And then when we add up the diagonal entries, right, we would get C times A11 plus C times A22 plus C times A33. And so factoring the C out from each of those terms, this is equal to C times the sum of the original diagonal entries of matrix A. So we can see here that T applied to scalar C times matrix A is equal to scalar C times the transformation of matrix A. So here are two linear transformations from maybe some more abstract looking vector spaces from the ones that we first took a look at earlier in the semester.